Good afternoon, evening. It's 4:40, 5 minutes earlier. For those that may watch the video, it won't matter to you. And for me, since I rode my bike, it's maybe going to be dipping under 40 degrees by the time I'm riding home, if the forecast looks correct. So I'll make sure I get my full gloves on because my hands froze pretty much last week. So I've turned back papers. I guess that'll be the first thing I'll talk about is I turned back sets 4 and 5, and I didn't put a link up because I just did this before I came in, but what I did is I have it under exams new and with solutions. I just simply, I guess I didn't update this page yet. Okay. I had to change my password, so I bet I'm not going to connect to the internet right away. All that talking I did, and I didn't pay attention to what I had to do. My password came is what happened a few days ago, sort of as a surprise because I just didn't get the normal warning that I normally get. So at any rate, now that I just updated my page, so it's underneath here. And this is just a continuation of what I did before. So probably the most important thing is you can look at 3, 4, and you can look at 5, and you can see what the points were. You can see in number 5, somebody exceeded by getting bonus points to push them over the top. The most important thing, though, is where we stand right now, and that's right here. And there's nothing particularly exciting about this in my mind. Why? Because the numbers just range from about 91 up to a little over 95. I mean, you might say, I want us all to be getting 99s or something like that. If there's no variation, that's not very exciting either. I mean, there is variation, and this happens to be where we stand right now, but I can tell you the standard deviation there says 2.11. As I punch the new numbers in and do the new totaling, it jumped from 3.5 or something like down to 2.11. So what does that mean to you? What would be your takeaway from that? If the standard deviation gets smaller as we get more papers brought in, what does that mean? We're all getting more and more clustered. It's tighter and tighter, and that happens all the time. I mean, I've seen it over and over again. That's just a statistical property of papers. Maybe it's the way I grade. I don't think so. I think it just means that the variations are getting out and it's tending to cluster on down. So I expect this will keep going. So where it's going to end, I don't know. I mean, what's going to be the variable is the exam will count a certain amount, and either 25 or 30%, depending upon the optimization I do. Generally, everybody weights it at 25% because you'll get more points from the final project. In the final project, or the project average, I mean, the 2 projects, the one you're working on now and finishing, and then number 2, which will be much more straightforward than number 1. But if that gives you better average overall than the exam counting 30%, then that's how your calculation goes. I explained this. If you don't remember, it's on the syllabus. But at any rate, those will be the things, those variabilities that will come with the final, and can't predict. I just can't predict. Some people will do really well, and some people will have just a stroke of badness or something. They'll mess something. And I'm not saying that happens every time in here, but I've just seen that happen where something happens. So we're on Tuesday of finals week, so hopefully that's early enough that you're not burned out when you come to take this exam. Because I know from my experiences, if you had to wait till the end of the week to take a final, it always seems like you get really burned out by that time and you just don't do as well. I went to school at Michigan Tech, which is in the upper peninsula of Upper Michigan. It sticks off into Lake Superior. School of Mines is what it started out as, copper mining, and it was 250 miles from my home down near Green Bay, Wisconsin, and I had to find, in my earlier years, I had to find a ride home or carpool with somebody to get back home, and it was a bummer to be stuck till the end of the week with a final to take and then figure out how you're going to get home. I don't have fond memories of that, but it's always the same. When final exams are done, you feel really happy about it, and for 3 of you, this is your last time, right? You can cry, you can shed a tear, or you can say, thankfully I'm done, because you'll never do it again. I mean, you just never will. You'll never get an undergraduate degree ever again as your first degree, and it's over with. I don't know if it makes you feel sad or not, but I didn't feel sad about it. I was glad it was over with, but it is true, though. You don't have to go through that. As a graduate student, I was at different schools, and the undergraduates always stress out, and if you're a graduate student, you just don't think of it the same way. It's just, it'll never be the same. So any questions on this right now? This will keep, evolving a little bit. Set number 6 is out there. You will have a few questions from chapter 6. That'll be set number 7, and then there'll be a few more problems from chapter 7 and 8, which is a combination on the DFT and FFT, and those will be due finals probably that Friday before. I've usually had them due on Monday finals week, but because we have the final on Tuesday, I'll probably require you to have them in that Friday at midnight or something like that, and then I can put solutions out, and then you have some time to look at everything, and you'll have everything. And John, you always have your notes in here. If you're the only one that has the paper notes, since I'm thinking of it now, would you be willing to volunteer your copy to be shared during the exam so people don't have to burn paper?
Sure, if they come to my table and grab it.
No, because I'll bring a book in, or somebody else maybe wants to bring a book in. You don't all have to carry your paper book in if you got it, or who's got. Since I'm on the subject, I might as well get this out of the way. Does anybody have a paper copy of the textbook?
I do.
Okay.
And that I can.
Generally, like a desk right up here would be what would be the central point, and then you can come and use it since it's going to be open book, open notes. I mean, you can bring the stuff in that you have for your notes, but in terms of if you burned a copy of the course notes, not everybody does that, so you'll be able to have a crib sheet that you write up from the first exam, from the final exam, another one, and then your formula sheet too. But I can't let you access your electronic book with an electronic device because there's no secure way that I know of doing that. So you'll have to use the book, and maybe I'll throw another copy in my backpack and have 2 of those here at least, or maybe we'll have 3 of them, I don't know. So the next thing that we want to look at is just finishing a couple of things that we didn't do last time from chapter 5, and then I think I've got some things in Jupiter. So actually what I want to do, I never did this. There's not a problem like I'm going to walk through right now on exam 2, but there could very well be one on the final when I was looking over paper or exam and questions over the weekend, and I thought, oh, I could put this off. No, I should do it now because it was in this chapter. So the geometric evaluation, and it's just a back of the envelope type calculation, but it still makes a nice exam problem, because even though the final exam is in class with open notes and open book, it's not open computer. You don't have access to Python or anything. So what I did here is I kind of did in the mathematics right here in the notebook about what I was doing, but instead what I want to do is do it over here. And I'm just going to put this together right in here, if it'll cooperate with me. I'm only using this configuration of 3 zeros and 3 poles at 0 just because it was what's in that example, and that might be useful to you as well. So the geometric frequency response idea is to say you're at some point here. I'm just going to pick 3 convenient points. This idea is a lot harder to apply without using a calculator, but the idea is to just get an idea of what the frequency response magnitude would be, less a gain constant. So let's just suppose we have, from this pole 0 plot, we know that there could be an unknown gain k that doesn't show up in the poles and zeros, but we have something along the lines of z minus, oops, stupid things. I'm going to erase this because I've already ran out of space by not doing things smartly. So according to the pole 0 plot, there's 3 zeros, one at minus 1.2, one at 1.2j, and one at minus 1.2j. And there could be a gain k in here, which I'm just going to say it's equal to 1. On exam number 2, one of the problems I've already picked out, I'm pretty sure I'm going with it, you're going to have to solve for k. And in that particular case, in that type of problem, I'll explain what you're doing. But it can be that k might be determined as an unknown, given that, you know, I'll just give an example. I'm not going to work the math here, but you could say, suppose h of 1 is supposed to be equal to 1, so the DC gain, that's the 1 up here, is z equaling 1. Which is e to the j0, or DC, right? You could solve for k based on what's going on in the 3 zeros over there by just plugging in z is equal to 1 and then getting some ratio of numbers times k, and then figure out what k needs to be to make you get 1 for the composite. Does that make sense? Okay, good. I covered something that if you have this a problem similar to this idea for exam 2, you'll know what to do then. But at any rate, I'm just going to assume it doesn't exist, actually. I'm just going to assume it's equal to 1. So the geometry idea is just saying, how can we find what the magnitude is at 0? So that would just be finding the length of the ratio of vectors, magnitudes. So, and then of course there's vectors from the 3 poles, but in this case those are all equal to 1, so they're not doing anything interesting. So we have the pole at minus 1.2 is minus 2.2 away, right, from e to the j0. You agree with that in terms of vector length? And then the next term in there is going to be the square root of 1 squared plus 1.2 squared. That's going either to the 0 that sits down below or the 0 that sits up above. That's just the hypotenuse of the triangle. Simple geometry. Just think that's what we're doing, simple geometry, to find the ratio, because that's what we talked about last time. So the other 0 sits in the same position, only up above, but its magnitude or length is the same. So it's 1 squared plus 1.2 squared. And then, like I said, in the denominator, there's 3 vectors of length 1 going to that point, and that's just 1 when it's all said and done. So here we've got, I'll do it differently. And what did I do that for? I don't need that either. There's no minus sign in there, because we're talking about a magnitude, so that's not good for them. So the 1 squared plus 1.2 squared is going to be 1 plus 1.2 squared, after we take 2 of those into account. So, I don't know, I'm going to do this really crudely. I picked bad numbers. They were good numbers in Python, but they're not good numbers in right here. But I'll just use my calculator on my phone. I happen to use the Hewlett-Packard style reverse Polish type of entry because it's the calculator that I learned on when I was in school. I mean, it's just convenient. If you don't use Hewlett-Packard calculator, I have a TI calculator too, but so it's going to be 1 plus 1.2 so plus that, 2.44 times 2.2 . So I get 5.368. Does that sound right? So I'm gonna not extend this, make this more painful than it needs to be. But I just figured I'd want to do this because I had a flashback, which happens, and now my pen quit working too. Had a flashback that if I do this on the final exam, I had a flashback from last year that somebody didn't get it right on the exam when I meant it to be kind of an easy problem, and we had never gone through this in class, so. Could be that my stylus just died, I don't know. Okay, let's see if I can get it working. Okay. Okay, it started working again. So now when we're, say, up at this upper point, which is right up in here, we have to erase the green lines, which I don't really want to have to erase because I already drew them in there. But now we have, all the lines are going from the various poles to this point. So one of them's right here, the other one's down over to here, and the other one's from out over there. So there's three different types of vectors, right, geometry-wise. So one of them is the one that's onto the real axes is 1 squared plus 1.2 squared. And then the one that's really nearby, that's sitting just at 0.2 above, that is 0.2. Then the one that's the length of the vector from down there at minus 1.2j, that's minus 2.2 away, or just magnitude-wise, it's 2.2. So I just have to plug into that, do that product, because again, in the denominator, there's 1. Now, if the problem has a pole in it that's not at 0, then you have to work that into the problem differently, right? Does everybody understand that from the geometry idea? That if the poles were not all 3 at 0, one pole was somewhere else, then you'd be drawing lines from each of the individual poles to get their vector length into the denominator. The idea in this is you're getting a quick idea just from a few points what's going on, and it can be helpful in understanding what the response is going to be like. I mean, fundamentally, we know that if there's a 0 close to the point of frequency evaluation, we're going to get a small gain or small magnitude. If there's a pole close to it, then we're going to get a large value because that's in the denominator, right? So that's the idea of the geometry in general, telling you, how you're either peaking in response or getting tied down. Remember I call the rubbery surface from last week. I don't know if that's weird or not, but to me it's like it's a membrane and it's been either pushed up or tied down by the poles and the zeros. So now I have to do this one separately, and this is going to be 0.375. Okay, thank you.
Where does the denominator come from?
The denominator comes from the poles. So I'll show you with another simple example. Suppose we had something like that and we had a 0 right in here, so we kept it in equilibrium. Then if we wanted to evaluate, say, right up over here, we've got that length, and then the poles also contribute their own lengths. So your magnitude response is going to have the product of the two black lines in the numerator, those lengths, and then in the denominator, the product of the lengths of the blue lines, right? Yeah.
For the phase at different points, would that be like the zeros minus the poles? Like the...
Exactly, yeah. And the angle has to be determined by the positive real axes. Mm-hmm. The angle that the line that connects from the plane on the on the unit circle to that pole, it's the angle that that makes. So for that particular pole, that's the angle that it's making in that connection. And those all get subtracted. I won't ask a question like that, but if you're wanting to figure out what the angle is, that's how you have to think about it. I'm generally just thinking in terms of the magnitude for this simple idea. I mean, in reality, I don't do this because I use Python or some other language, but, you know, and if you're wondering how this comes into play and what's in the Jupyter notebook, it's just I just set it all up so I got the proper vectors in here, and I used a function from linear algebra. I imported I used the linear algebra sub-package of NumPy, and there's a function called norm in there, which you can put a complex number in it, and it finds the magnitude of the complex number. I just chose to use that for whatever reason. I did that in here. So here I'm finding those different cases were done here just by using this idea of the numerator and denominator. And there was no denominator in here because it's 1 all the time in this particular problem. So what was I looking for? The answers are in here if I just grind this through, but I didn't do it. I mean, my computer restarted this morning. I guess they're still in here, though. This is the one we just did, right? The last one? No.
Because that's at 0.9 now.
Is that the one? Or did we not get the same answers that I had in here, now that I'm looking at it? You get 0.375.
One of the zeros is inside the...
Oh, in the example?
Yes.
Okay. You're right. Okay. I didn't copy it correctly, so you got a different problem. Oh, well. You get the idea, though, I think, right? Okay, so I'm done with that. Just sort of an overview. We looked at all-pass filters in Python, and now we're going to go back over and look at I guess since we're on the Jupyter side of things, this example in the notebook is for text problem 521, where you have, I think, a 5-part problem that has all these different input-output relationships where you're doing things with upsampling, downsampling, and maybe a filter block inside of it, and you're supposed to tell me what the filter is, whether it's low pass, high pass, band stop, or band pass. And the idea here was you have some primitives so that you can use these in the modeling if you want to. I did that myself in my solutions, but most people will just figure it out by sketching the ideas, and that's what I would prefer you to do. This is sort of a last resort if you don't trust your sketching or just want to be extra confident. You can do that. Here we take a triangular shaped spectrum, put it in, and I have defined a filter then, and it's creating the little house shape, and then you downsample it and it stretches it out. That type of thing. since I'm thinking of this and since you haven't turned in the homework, I want you to remember that what constitutes a bandpass filter or a bandstop filter in DSP, just for example, since I've got this up here. If the filter had a response in this interval and had a response, say, in this interval before you got to the folding frequency, but it was 0 in an interval between 0 and 1/2, what type of filter is that? It's a band stop filter, right? And the band pass is the complement of that. But so be careful when you're thinking about that, because I don't want you to misclassify what you're seeing. So the 0 to the folding frequency is where the action is, and if it looks like it's got two regions where it's high and one region where it's basically nothing, that would be band stop, and of course the complement of that would be band pass. And high pass is with respect to the folding frequency as well. We're not to linear phase yet, but we will be, so that's what this is for. So now we want to do is finish up talking about minimum phase systems, and then we'll go into generalized linear phase and then linear phase systems. So minimum phase, remember from last week, was just the special condition where the poles and the zeros both are inside the unit circle. That's minimum phase. And because of our definition of inverse system, we know that because both poles and zeros are inside the unit circle, the inverse does exist for a minimum phase system. So we looked at that in an example last week. There will be a problem on this on the exam that will involve a little simulation and verification of what's going on. But the idea is, we're going to look at it right in that example again now, is that if you want to be able to create an inverse for a system and it's not minimum phase, you can create the inverse of the equivalent minimum phase system by moving any zeros that are outside the unit circle inside the unit circle, putting in a gain adjustment to make sure that you don't alter the gain, it's effectively like the DC gain, and then take the inverse of that minimum phase system as your equalizer, and that's coming up here in example. And of course, we already know that you can write any system as a cascade of a minimum and an all pass. And what we're going to see right at the very end is you can go over here and say, equivalently, we're going to have this a little bit later. So we can also do it with a minimum phase and a linear phase to create an equivalent, to create the same H of Z system. So those are the two kind of takeaways in this whole area of what you can do with minimum phase to synthesize a generic system, either in terms of with an added all pass or with a linear phase. But right now we're not talking about what the linear phase is, so we'll get to that later. So the basic idea that the book talks about is, and this is an example that says, suppose our system has a component H1 which is minimum phase, and then it has 1, 0 sitting outside the unit circle. So how are we going to make this into a minimum phase system? Is we're going to modify this by putting the 0 inside the unit circle, because the assumption here is the magnitude of C is less than 1. So when we formulate it like this, C to the minus 1 minus Z conjugate actually has its 0 outside the unit circle, and we throw it back inside the unit circle. And then to keep things in check, we're going to put that added term in the denominator, and we're going to put the original term in the numerator. So effectively, it looks like we haven't done anything. We just simply temporarily created something that makes this look like a system that's composed of a minimum phase and a all pass. So in the green brackets there, that's just the all pass system that we saw defined earlier. And then the book has this example where it's got two zeros that are outside the unit circle, a pole that's inside the unit circle, and it says make this a minimum phase system with an all-pass decomposition. And the first part of the exercise is to go ahead and factor things to look like this form that was done right up here. Mouse is really sensitive. Oops. So we start with that, but now we're going to replace it with that. And that's what's done here. These have start like this, and then down here, they've got it factored the opposite order, where the z to the minus 1 is first, and then the z conjugate is second. So it's looking like, or the z is second, or c is second, I mean. So these are already setting it up for the zeros that are inside the unit circle. And when you do this rearrangement here, you end up having a factor that comes out 3/2 in this case. And this is where the gain comes into play to make sure the gain is adjusted properly. And if you work a problem like that, you have to do that. If you work a problem like that on exam 2, you have to do that to make sure it comes out properly. So just stay tuned into that idea. That's where it comes from. The simple idea, the pictures that I introduced last week, and we'll be looking at more again tonight, is a sketching of the basic idea of how you are reflecting zeros inside from zeros that are outside. But the thing about the pole zero plot is it doesn't show you gain, the DC gain term. It's not able to show this. So you can sketch it and make it look right in the pole zero plot, but you still have to make sure that that's included properly. Otherwise, it'll be wrong. It'll have the wrong gain, DC gain. So this problem just carries on, and so it has the minimum phase equivalent as the first square brackets here. And then it's added back in the maximum phase zeros are sitting right up in here. And then it's added in the minimum phase poles to make it an all-pass section. So that's how that works. And the all-pass section, by definition, does not contain any gain constant, because the all-pass section has unity gain by its definition, right? We've kind of proved that last week with that geometry demonstration. So that's how you can mathematically work a problem, and this idea is useful, like I said, in some of the homework problems, and it'll definitely be helpful in one of the exam problems too. So here's the 3 different pictures of it, and this is what I was talking about last week. If this is your H of Z system, without being able to demonstrate the need for, that, because that doesn't show up on the pole zero plot, you can start over here and say, how am I going to create a minimum phase system? You're going to take the H of Z system and you're going to reflect this inside. And that's all you have to do to make it minimum phase, right? You just have to take the conjugate reciprocal of those zeros to get it inside, And then in order to make things balance out, you construct the all-pass system to have poles sitting where those zeros were. So the poles that are in your all-pass system are the ones that will annihilate the zeros inside the unit circle if you cascade these systems together. And then, of course, the zeros sit outside the unit circle where they are in the original system. I don't know if you think not hard enough about this too casually, watching TV or doing something else, you might get convinced to say, "What is this? This doesn't make any sense to me. You're just playing a shell game with me. It's not doing anything." The idea is you're synthesizing something. So to say that the product of this system with this system equals that system is what this is all about. And when you take the product, if this is the same place as that, of course it's going to go away. It's going to cancel, and so on and so forth. But the idea is, if you want to get your hands on the minimum phase system, you have created that from the original system. And if you wanted to know what the relationship is to connect the two together, that's the all-pass system that does it. You can't build an inverse all-pass system, though, because that's not realizable, right? Because an all-pass system always has the causal and stable all-pass system, the ones that the book talks about, always have the poles inside the unit circle. They have to be there, right? You should be very, very much, if you think about this, you should be like, I can't do that. I can't ever have the pole go outside the unit circle if we're talking about causal and stable. But the mathematics lets anything happen. I didn't show you, and I didn't show you, Freak Z, for example, or that graphical application that I wrote. Remember, I could move the poles and zeros around. I could move them outside or inside. It doesn't matter because it doesn't know that it's causal or not causal. It's just evaluating the math of the magnitude response. And Freak Z is that way too. If you put in poles outside the unit circle, it'll produce a nice stable frequency response. If you put poles on the unit circle, it's going to be upset though, because it's going to try to evaluate infinity or zero. It's going to try to evaluate a point that's 1 over 0 at that point. It's going to have a problem, but it doesn't have that ability to understand that. But we have the brain that says, no, we can't do that, and we're not going to be able to build that. Okay, so now this is getting back to the idea of that I showed you in Python last week, and there will be a problem related to this idea on exam 2. Frequency response compensation. So in this, even in reviewing it myself, I get a little bit confused about the notation and the terminology. This is an example that is in the book, though. From very, very, very long time ago, when Bell Telephone was inventing twisted pair phone connections to all the households, they knew that there was some equalization that would have to be required on all those wired networks. So they had to come up with a way of equalizing the phone line so that parasitics and other things with the twisted pairs would be managed accordingly. So they knew about equalization in the analog domain long before anybody wanted to do it in DSP. And equalization is still needed in digital radio telephony today, but it's done in DSP because that's the way the cell phones work. But it's still the idea that you might have a non-minimum phase. So here, the assumption is HD is supposed to be the distorting system. So HD is the distorted waveform, and SD is, or HD is the distorting system, and SD is the distorted signal as a result of going through some system that's altering the frequency response. So we'd like to recover from SD, the distorted signal, as near as possible the original signal. So that's an application for wanting to implement the inverse of the system so that you can wipe it out. You know, in other words, h of z times 1 over h of z, if you can implement it, cancels out and you have 1 back again. But in this situation, we have to do it with a minimum phase equivalent of the system, because if the system is not realizable, because if it has a 0 outside the unit circle, it will have a pole outside the unit circle as its inverse. So they talk here about creating the minimum phase system, and they show it here with H min being the distorted system divided by H all pass. And it's basically just taking the original equation, which said times the all pass. I got an extra line in there somehow or another. No, that's my parenthesis. My pen started acting weird when I got near the edge of the screen. At any rate, just moving the H all pass in that equation to the left-hand side. And in this case, the only thing we're missing is there's a D in here for the distortion system. So that's where this equation is coming from, though. So we're going to take and form a new system called the compensated system. So it's going to be HD of Z, the distorting system, and then we're going to cascade it with a compensating system. And that compensating system is going to be 1 over H minimum. And if I get myself confused, I just have to go back to thinking that's what it has to be, because we have to put an inverse in, but it has to be an inverse that's minimum phase. And we know once we have synthesized H min, we can flip it upside down or invert it, and we're safe, right? Because poles and zeros are inside the unit circle. Is that clear enough? If you find your brain wandering away, just go back and think, what do I know I have to do? I have to create the minimum phase equivalent. And because you're going to do this with a simulation involved in the exam, you'll know if you don't have the gain scaling constant right, because you're going to see a waveform that doesn't have the right amplitude on it. It'll get either bigger or smaller if you get something messed up there. So you'll be able to do that, understand if you've got that part of it right. So G of Z ends up being just the all-pass response. And now I know clearly why it had to be set up the way it did, because an all-pass that relates the minimum phase to the system is always a causal all-pass. So this has the poles inside the unit circle and the zeros outside the unit circle as needed. So now we can go back and just briefly look at this again. In this case, there's a pole sitting out at 2, so we have to create the minimum phase equivalent of this, but we had to set the gain right. And I didn't do this example with that gain factored out accordingly, so I had to add it in later. But it's going to be a pole, the 0 is going to be at 1/2 rather than +2, and then we'll have to put in a factor of 2, because if we were factoring this the way that previous example in the notes was doing, this 2 would have come out front. 2 would have come out front, so we would have had a 1/2 sitting over here, and that would have been, well, -2 would have come out, and then you would have had the z to the -1 minus the 1/2, c to the -1/2. At any rate, that's what we end up doing. So here I'm forming all 3 systems. The numerator and the denominator for the first 2 are as defined, with this being the compensation part, -1/2 instead of 2. and then I convolve them together to form the cascade for the numerator, or the denominator and the numerator, and then all three of those responses are plugged in using this function I have in the module. You get that when you import IIR Design Helper. It's got that function inside of it. It allows you to cascade responses. You can see that I'm using IIR _D to get access to that function. And just like anything in Jupyter, we can just see how it's set up to work. I created it for cascading filters in general, and it's useful here because I can compare all the responses. So here, what I had to do to get this to work, I had to put in a 2. And why am I not seeing it right now? Oh, it's the wrong problem. I had to put in a 2, and I put it in right here into the cascade to get the unity. So if for example, if you're working the problem and you don't factor like we should have, this had to be put in the denominator, and so the gain is higher than it should be. The green line is the cascade. So that fudge factor had to be thrown in there to make that work out. Interesting thing about this is if you go on and look at what's going on, like if I look at what the distortion effect is, the gain is nice and flat, but in particular, suppose I turn it on with the option group delay. You can see that the group delay, which is the green one, the compensated system, has not got a constant group delay across the band. So we still have some distortion due to non-constant group delay, but in the case of the equalizer, this still can be beneficial. And the exam problem, you'll understand when you do it, because it's kind of cool the way it works out. You'll be drawing a picture, so you'll be seeing some benefit to it. It's not as perfect as the totally distortion-free, but it's pretty nice just the same. Because based on what we've been going through, this, if you look at magnitude in phase or magnitude in group delay, let's just say we're doing magnitude. Magnitude was flat in the cascade. Great. Group delay should be flat in the band of interest, and over the entire band it's not perfectly flat. So we haven't made it perfect. It's got that a little over 2.5 samples of group delay down at the low frequencies. We can talk more about it after Thanksgiving when when the exams will be done. It's pretty cool though. I think it's being able to play with something is nice to do though. Question?
Yes, so the system numerator is 1 minus 2b to the -1, but then you just multiply by 2. It doesn't make a difference if you multiply by -2 instead of -2.
Good point. Yeah, it probably should be -2. It will change the phase, so let's just do that. Make this right.
I was also wondering why A3 that we multiply by...
Actually, yeah, let me take care of this first. It didn't change though, did it? Yeah, in my mind, just the phase response would change. So keep going. You had another question, and I didn't let you ask it yet.
I was wondering why A3 that we multiply by 2.
Why didn't I multiply by 2?
No, why is it that it's not A1 or A2, but A3 by 2?
It should actually be in the inverse is where it should be. I just put it in there. It should actually be in the inverse is where we should want to put it, I think. I just threw it in there somewhere because I knew I had to throw it somewhere to make the gain go to unity. So I just put it in somewhere. But if it was in A2, it would show up the same way though, right? Because they're in the convolution. And if you're convolving two things together, two polynomials together, that gain constant will transfer across in the convolution. So I just threw it out there is what I did. So maybe I didn't do as clean a job of setting this up. This was kind of an afterthought, but I did it for a reason though, because I wanted to be able to talk about it now, and then I wanted you to be able to have something to look at when you're working the problems. Is that good for right now? I might think about it and get inspired if I'm tonight and want to change it, but I think I'm just going to leave it. You know it's not perfect. You can make it perfect, though, by fixing it yourself. So how would you do that? You would go back to that example problem that we were looking at in the notes, and you would just do exactly that. So the way to get it perfect would be to go up into here to this example. This is what I always go back to. I'd say we started off with that. We started off with a 0 that was outside the unit circle. So the first thing we did is we factored it so that it became this. And in doing that factoring, we had to take 3 halves out of there. And that's now in h of z. And then that 3 halves would show up in this term in the square bracket, and that's the minimum phase system, and that's where you'd want it to be. So that would be, that would either be in B2 or A2, whichever polynomial you want to put it in, numerator and denominator, right? And then it would be done right. So I should make it right myself and then resave it, but I'm sort of a hacker at times. It's like I'll do something and I know I'm missing something, let me just draw a picture, and then I'll look at it and say, this will fix it. But if you needed to document it, it wouldn't be done cleanly because it would be incomplete. Okay, moving on. Talked about frequency response compensation. There is another more detailed example that's in the notes that I think is in the book too, compensation of an FIR system. And this one, it's all zeros, so 2 of the zeros, one conjugate pairs at 0.9, another conjugate pairs at 1.25. So here, I guess I quickly put it together because what I did was I had to take that and then reflect the 0 to the inside, and then that becomes, you know, these 0.8s at an angle plus and minus 0.8 pi, and then run the response curves out. And here, I did this probably in MATLAB a long time ago, but I think, like I said, I think it's in the book. The interesting thing you can get out of this, though, that we're going to be seeing one of the properties of a minimum phase system. The original distorting system has quite a bit of amplitude fluctuation in it and quite a bit of group delay fluctuation in it in particular. So the non-minimum phase system has, you know, quite a wide swing of group delays in it, whereas I'm going to go down here to the minimum phase system, it's smaller. It's not as, you know, it's just crossing over 0, whereas this one's crossing up to about 8 or so, and it's going down to -8. Here it's still going down to the -8, but it's not, it doesn't have as much variation in the group delay. And in terms of the all-pass system, it's got 0 dB gain, and it has a fairly good amount of group delay in order to synthesize group delay in order to make the minimum phase go to the original system. You can make different comments about it, but we're going to look at the theorems next, which just tell you what happens that makes the minimum phase system desirable. So that's properties. Minimum phase-like property, I'm not really going to prove it, but there's a sketch of it here in the notes, and it's talked about more in the book, too. It just says that for a minimum phase system compared to any other system that's not minimum phase, the phase lag, or the amount of phase in the non-minimum phase system, is always greater than the minimum phase. And I didn't comment on that, but I commented on the next one, minimum group delay property, just taking it to the next step. In the group delay sense, minimum phase system also has the minimum group delay. So that's the one I was talking about. So that's number 2 of these theorems. And then the third one is the one that I think hits home to me, being that I play music and I think about phasing and things. A minimum phase system has what's called the minimum energy delay property. So if you look at the impulse response of a system, little h at 0 would be the DC, or the t or n is equal to 0 value. That's going to be less to the minimum phase impulse response, magnitude-wise. And if you look at the partial energy and summing up from 0 up to some value n for a causal impulse response, that the energy of the minimum phase system accumulates the fastest. I think I say that in words down here. Maybe I don't. I do right here. Minimum energy delay is delayed the least, and they accumulate the fastest. I guess I didn't say that in here, but it's like the signal enters the input and it gets to the output with all of its energy faster than any other system. So it's got minimum time delay, and the energy arrives the soonest. So it's like if you're going to get blasted by an energy weapon or something, and it was going through some process that was going to minimum or maximum phase delay it, the minimum phase would get it to you the fastest. You would feel the effects of it immediately. Or in terms of processing of signals or music or something, the signal arrives the fastest, and there's less phase interaction because of that fact. Because time delay means that something can interact with something else and create some sort of a destructive interference. So there's a problem in the book, in the notes, a problem I did not assign this time, but it related to this example right here. Just a 4-0 system looking at all the possibilities. The minimum phase is the top left, top right is the maximum phase, and then the two below it are the mixed phase. One pair is outside, one pair is inside. If you go ahead and get the energy from the impulse response, in other words, you have to inverse Z-transform that system and get the impulse response. It's a 4-tap FIR filter, or 5-tap actually. So it's a 4th degree polynomial. And you see the minimum phase starts out at 1. All the others start out less than 1. That was that H0 property. And then if you accumulate the energy by summing the squares of the impulse responses as time marches on, you see that the minimum phase system rises up and stays up at the top. They all transfer the same amount of energy. It's just which one does it the fastest. So that's, to me, very clearly shows you the idea of the minimum delay property in terms of minimum phase. Maybe it's exciting, maybe it's not exciting. It's just something new. I think, John, you asked me what makes this so exciting. It has a bunch of little neat little things, but you're not going to go on an interview, let's say, because we were talking about that before class started, and necessarily find somebody that wants to talk about non-minimum phase systems, but they're obviously desirable, though, if you can make it work. But in a physical situation, you don't have a choice, right? I've mentioned multipath fading in telecommunications. It is what it is, and you can't move around in the room to get it to go better unless you have some indicator on your phone that says your equalizer's struggling because it's not minimum phase. Could you please, move 2 steps in this direction and see if it resolves? I don't think most users would want to do that, but that does make me think of something, though, that I've been reading about lately that I had not really read about. You know that location is something that's, like in my family, we share the location information on our iPhone, so I can see where anybody in my family's at. And you can do it on Google Maps, too. But Bluetooth has got the capability to do that right now, and it's being talked about in some of the articles that I've been seeing on my emails lately, that they're going to add that feature. And so it's just more ways of figuring out where people are at, like where are people in a building right now. Somebody could have that information, and we could know there's 5 of us in this building or in this classroom. It's drilling deeper and deeper if you have a device. If you don't have anything wireless on, you're probably mostly clean, but if you have something on that emits a signal and they can get some handle, then you're going to know you're there. So the next topic is systems with generalized linear phase. This is the end of the chapter. It's probably the most exciting thing, actually, because it's the basis for FIR filters that we use today and what makes them so popular. So first off, we'll talk a little bit about it and then take the break. What is an ideal linear phase system? So an ideal linear phase system you could draw out as this picture and just say that you can have whatever magnitude response you want, and the only phase you have associated with it is a linear phase. That's just the phase sloping down, which we know is what we get for just a fixed time delay. It would just be a constant delay over all frequencies, the same value. That's just the wish, and that's sort of like the reference point. The ideal low-pass filter would then look like this picture. It would just have, in the pass band, it would just have that alpha, that phase slope. And if you were thinking of it in terms of the sync function for the impulse response, it would just be an alpha sample shifted version of the sync function. But we know we don't implement that as a practical real-time filter because it's not causal. But if you could get away with that, or if you could do it on a recording, then this is what you would do. If you wanted to ideally low-pass filter something, you could do it during playback. Does that make sense? In a lot of applications, that might be what happens. That might, be an application where you need to do that, or seismology people might do that on captures of seismic events, nuclear tests, et cetera, et cetera. I can't say I know one way or the other. I can only speculate that things like that can be done, or searching for oil as well. So this also makes clear that alpha could be any number, and if you want to make alpha non-integer, then you're going to have samples of the sync function that don't have all the nulls and peaks synchronized with samples. So we talked about ideal linear phase. Now we're going to get into something a little bit more practical, and that's going to be generalized linear phase. And this just says, okay, we were asking for too much. We can't make the ideal linear phase. We'll just say we can have a real function of omega times a linear phase plus a fixed value of phase beta. And that's what the FIR filters we're going to see after the break can do for us. So we can settle on generalized linear phase. That's pretty good. And I think there's a whole homework problem. I think the last problem asks you to look at these pole zero plots and then comment on what are you seeing. Are you seeing minimum phase, all pass, generalized linear phase? You know which problem I'm talking about, right? So, and I'll take questions on that problem too, because I think we're going to finish early today. So I'm thinking of where we're going right now. But let's take the break, and we're going to take off from here and then get to the linear phase filters that we use for design all the time. There's a big bump we have to go through, and that is we can't design the filter. We just have to get over that hump and have something that we know is designable and then run with that. So if you don't want to take a break, you decide. When you come back, we'll get started again. I'm going to pause the recording now, and I'll take questions if you want to. I may start eating, though. Okay, we're back from the break, and I've got food in my mouth because I didn't get to take the opportunity to eat some energy food. So we're going to talk about generalized linear phase, and then we're going to head over to how to make filters that have symmetry properties, FIR filters that obey the generalized linear phase. So we have the alpha, which is the linear phase component, and then we have beta, which is the constant phase, and that's incorporated into generalized linear phase if you want to have certain types of filters which have 90 degrees phase shift, for example. In communications theory, an example for that is single sideband communications, not super popular anymore, but it is a special type of filter. It's called a Hilbert transforming filter if you go with that option. So if we write these conditions out and we take this general form, we have the A is just a real, but it can be bipolar. That means it can change sign, like the sin x function. The sinc function changes sign, right? But it never becomes complex. So it's a real function, possibly bipolar. I better be careful when I say that. And as engineers, I know what bipolar means, but it's a disorder, right, for some people. So if we put that together into an equation, we can write out what the magnitude, what the frequency response looks like in terms of the Fourier transform, dTft, of an impulse response, h of n, and what the desire would be to come up from this condition, what h of n has to be. And if we write that and combine those things together, this is what the equation says. We need to be able to find an h of n that will make this equation equal to 0 for a given value of alpha and beta. Now, engineers like hard problems, but this is not necessarily a problem that you want to have to solve. It turns out it's a necessary condition, but it's not a sufficient condition. So it's not really a design equation. It's not anything that we can really take advantage of. So we sort of hit a roadblock right here and say, okay, what happens if we just specialize it to FIR systems and not try to solve such a massive problem? And we also throw in that we want it to be causal. That would be a nice thing too, right? And you've implemented these filters already in the DSP lab, so you know they really worked, right? I've got some example results in the notebook that I put in there from lab measurements taken years ago. So this is what the generalized linear phase equation looks like. If it's causal, we just started at 0. So what has been established without having a rigorous proof is just that there is a possibility that works. and that possibility is symmetric coefficients. So if we create symmetric coefficient filters, then they can either be even symmetric or odd symmetric. Then we can get the generalized linear phase. So this is maybe not the really elegant thing to say, but it's a reality. This works, and this is very popular and very much acceptable. So go down this path so far and just sort of jump over and say, I don't know how to solve this problem, but I do know that people arrived at this many, many years ago, like in the 70s, maybe earlier, that symmetric coefficients works. So as the first example, if we have a symmetric coefficient filter where from tip to tail the coefficients are equal to each other, and then they're, from the edges all the way to the center, they're symmetrical. The center can be onto itself if it's an odd length filter, and if it's an even length filter, there is no center tap to worry about because that's a half integer. It doesn't exist. And if we do that, the frequency response ends up being some real function that's even, and there's a phase shift, a linear phase, m/2, like for our alpha. We can go with odd symmetric coefficients, and that can be shown to be the same thing, except now we have beta showing up in order to make that work. And odd symmetric just means what's at the end, equal and opposites at the other end, and as you step in, it's always equal and opposite as you go along from the endpoints. So this is sort of like the beginning of the whole section now from the practical standpoint. There's 3 or 4 types of FIR linear phase systems. This first heading is for the type 1, but I'm just saying if we were to start here, we would just say linear phase filters can be made using symmetry, and there's 4 different types. There's type 1, 2, 3, and 4. And it's confusing to me, but you'll have notes when you take the final exam. I'm not doing anything with this on exam 2, where you have to know type 1, type 2, type 3, types 4, but there's properties of them, and there's some nice notes in here that talk about that. So type 1 is symmetric, and M is even. So that's an easy one to remember. It's probably the most popular one. But notice, though, that we start at 0 and go up to M. So that means, and since we're all coding in Python, if we go from 0 to M in Python, that's a legitimate array type starting at 0. 0 to M is actually going to be how many points, though? M plus 1. So this is actually an nth degree polynomial that has m plus 1 coefficients, because that's the way polynomials work, right? You have the constant plus all the various powers of the variable. So if we go ahead and find the frequency response of this filter, this is the generic result, and now what you do down below here is you say, oh, we can take advantage of the symmetry. We can just have a sum going up to the m/2 minus 1 point, and we can bring in these coefficients, and they're equal to each other because we're bringing them from opposite ends of the filter. So that collapses down, and then the first coefficient right here is the center tap, because when you have m even, there's an odd number of points, so there is a center value. The m/2 point is going to be an integer. So when you put that together, you can start seeing how this comes together to form some real function. So this will be because it only involves cosine of omega, and the filter coefficients are assumed to be real. So if we define a new set of coefficients, A coefficients is just, instead of H, then this is what the frequency response looks like, where the A coefficients are related to the original impulse response coefficients. And the conclusion is that alpha is m over 2. That's the fixed delay that the filter introduces. That will be the group delay of the filter, m over 2. And beta is either 0 or pi. But in most cases that I'm work with, beta is 0. And then you can go ahead and go to the type 2, where now m is odd. So that means that there's an even number of coefficients. So half of them are on one side and half are on the other side, and it's symmetrical, and there's no point in the middle because it's even, right? Because that would be an odd half integer. And that works out with a cosine. Again, it's just that you don't have the central term like we did here. You don't have that center tap term. And then for type 3, we can have the odd symmetry with m even again. That's type 3, but odd. And then type 4, m is odd with the odd symmetry. So I know if you've never seen this before, and I'm assuming you've never seen it before, you're probably saying odd, even, there's an odd and even length, and then there's an odd and even property, the symmetry of the coefficients that's running around here. But for me, I like this picture. This picture kind of makes it easier to figure out what's going on. If you've got a type 1, then you always have a center tap at m over 2, and then you have the symmetry from the ends moving towards the center. If you go to a type 2, which is the upper right, it doesn't have a center tap because m over 2 is a half integer, so a point doesn't exist there. You just have the coefficient symmetrical from one side to the other. And then type 3 has a center tap, but you have to force it equal to 0 because you can't do anything but have it be 0. I mean, 1 and minus 1 are odd symmetric. 0 is odd symmetric with itself. So it has to be set equal to 0. And type 4 has a half integer there, so there is no point, but you have the odd symmetry. So those are the 4 possibilities for the types. And they all have to do with how you're designing it. Low-pass filters will generally be a type 1 or a type 2. High-pass filters will be a type 3 or a type 4. Not necessarily, though. I'd have to look at the examples. You can tell by looking at the poles and the zeros, though. That's another really cool thing, and we're going to see that, how that works out. So if you go to the math for the type 1 and type 2 systems, we have symmetric, and it's either even or odd length. So if you write that out and look at what the symmetry condition imposes, h of n versus h of m minus n, and reduce that down, you can sum from m to 0, h of k, z to the k minus m, and that's just by incorporating that into the sum here. And the bottom line is you end up with these 3 things to look at. H of z is equal to z to the minus m times h of z to the minus 1. So what does that do? It says in particular that if you have a 0, a z0 that you found for h of z, in other words, that's a 0 in the polynomial, that if you plug that in, it says that h of 1 over z naught must also be a 0. So then that, and I'm kind of skimming over this a little bit, but the next observations here are if the 0 is not on the unit circle, and the angle is not either 0 or pi, so it's not on the real axis, then we know that the 0 has to occur somewhere in the complex plane. And if the coefficients of the filter are real, which we assume here, that means that we actually have no choice, according to the rules for the type 1 and the type 2, to put down 4 zeros at once. My wife had twins, so I always think of twins, and this is quadruplets, right? It's like if you're going to give birth to linear phase zeros, you have to give birth to 4 at once. You don't have any choice because the constraints in the math we were just looking at, you know, the conjugate symmetry says the zero, z0 and z0 conjugate, that's the normal thing for coefficient polynomials with real coefficients will have conjugate roots. But then the symmetry property imposes that z0 must equal 1 over z0 conjugate, and z0 conjugate must also give rise to a 1 over z0. So it's this quadruplet idea. We have to put down 4. They occur in clusters of 4. Okay? You're just taking the facts, but these are the facts. The next condition is if you're going to put a 0 on the unit circle, then they can occur just in conjugate pairs. You don't have to worry about quadruplets because if you take the conjugate reciprocal of the 0, it is itself. So it doesn't force you to have to do it onto itself. And if you go and assume you want to have a 0 on the real axes, then you have to have the conjugate reciprocal of the real number, which is just the reciprocal. So if you want to place a 0 here, you're going to place a 0 out there at the reciprocal. And finally, if R0 is equal to 1, in other words, it's on the real axis and at radius 1, it can satisfy all the conditions, so it can occur by itself at either 1 or minus 1. So a single isolated 0 could be at 0 or minus 1. You're free to do that, and that does not violate the symmetry conditions. If you go with the odd symmetry, which is the type m is equal to 2, not the odd symmetry, but the odd length, odd value of m, then this condition gets forced on us, and then it says that we have to have a 0 at z is equal to minus 1. It says h of minus 1 is equal to 0, so you have to put a 0 out over here. I have a table that shows a picture of this at the end too, because I just need the picture to make it all make sense to me, because I'm just rambling on stuff. It's like you're learning all these kind of strange rules. In the type 3 and the type 4 systems, because we have to have the minus sign involved with going from one end of the filter to the other, you're forced into always having a 0 at z is equal to 1. And that's from the reality that how can we make minus a number equal the number itself? 0 is the only thing that suffices that, right? So we have to put it there. And if you're thinking of z is equal to 1 is like DC, right? When we sweep around the unit circle, we start at z is equal to 1. So a filter that has a 0 at that location can never be a low-pass filter, because that's right where the pass band should lie. But a high-pass filter would be okay. Differentiator and some other things you might build with these filters are all okay. Now, if m is even in a type 3 or a type 4, and I guess it's type 3 would be m is equal to even, then have to have a 0 at z is equal to -1. That's forced, and that would mean it's not as good for a high-pass filter then, because that would be right in the pass band of a high-pass filter. So this is how I keep track of it pictorially wise. We still have the rule of the quadruplets, we have the rule of the twins, and we have the rule of the twins on the real axes and that sort of stuff. But if you look at type 1, 2, 3, and 4, we see how type 1 is the most bare bones. They have to abide by the rules of the quadruplets and pairs if they're on the real axes. And if they're on the unit circle, they can be conjugate reciprocal. They're conjugate pairs, of course. If we go to the type 2, we have to add one more feature, and that is we're forced to add a 0 at z is equal to -1. And if you go with type 3, you have to add a 0 both at -1, z is equal to -1 and 1. And with a type 4, you just have to add the extra 0 at z is equal to 1. I don't expect you to memorize this, but you know that you can find out, right? Or if you're given a filter, if somebody gives you a set of filter coefficients, you plug in to it with z-plane, let's say, you'll be able to see, does it match this configuration? And you'll be able to make some assessment on that. So I played some games here in the notes, and I'm not really sure if it's worthwhile to go through these pictures. I have it in the Jupyter notebook, but I used to think it was a cool thing to do, but it's kind of silly in a way. Here I just synthesized an m is equal to 4 design. So I picked some value at 2, and then I picked some symmetrical values for 0, 1, and 3 and 4. And when I do the z-plane on that, I get what I expect. I get 2 pairs of conjugate zeros, but I could have gotten a quadruplet from this too, right? It's possible, but they were on the unit circle, so they didn't go that way. Important thing to note, though, is the phase is linear. It has jumps in it because jumps can occur when we have, say, zeros on the unit circle. We know that when we zoom past to evaluate the frequency response with a 0 on the unit circle, remember we get that jump. It can be either it's going to be 100, it's going to be a jump by pi when we go with a 0 right on the unit circle, and that's what's happening here. But the important thing is the slope is constant, and if we take the group delay and ignore the derivative where there's a discontinuity, we get a constant value. And it's exactly 2 because that's the center of the filter. You can think of the center of the filter as the mean delay of a signal going through the filter, and that's the group delay then. The mean delay is the group delay. So, does this sound okay? Here I'm picking a type 2, so I just laid down 4 values in its entirety. There's no center value, and this again doesn't work out really exciting. It's just got one real 0 that has to be there. That's a requirement, right? There has to be a 0 there for the type 2, and then there's a conjugate 0 pair on the unit circle. And I picked a few more examples in here. I'm going to move ahead to something a little bit more exciting. I'm going to go to we're going to look at this type of filter, the equal ripple low-pass filter, which uses the Remez function. MATLAB had the Remez function. They eventually changed things up in the way their filter builder works, but we have the Remez function, and that's how my Scicit DSP-Com FIR design helper uses the Remez function. What I want to look at that's here in the notes, this is like one of the most important last things to look at, is a type of filter that was arrived at a long time ago when people said we can do symmetrical filters. So they said, let's do a frequency sampling FIR design, is what this is known as. You take a certain length of your filter and you say, we are going to design the filter coefficients based on sampling points in the frequency domain at some desired amplitude. So we're free to specify, say if it's a type 1 system, we're free to specify the amplitude response at m/2 plus 1 point, because that's the way things are constrained with a type 1 filter. We have the symmetry going from end to end towards the center, and then the center value stands alone. So we can write a system of equations based on the response for the FIR, the type 1 filter, and this is what it looks like if we use the A coefficients for the filter design. We're just going to have m/2 plus 1 equations, and then we can set up these equations in a matrix form where we're going to solve for the filter coefficients A as C inverse times A, the frequency response points in a column vector. And you can actually do this with a DFT or an FFT. Does this make sense, though, that we could design a system of equations and then solve it as long as it's invertible? We should be able to force this, because we're not asking for more than what our means are, and our means are how many degrees of freedom do we have. If we have 10 degrees of freedom, we can then back that into the design of the filter, and that's what this thing does, and that was what this example created. In my Scikit DSP COM, I don't have frequency domain, frequency sampling design, but it is in scipy.signal. They've got frequency sampling design. And again, because it's symmetrical, it's going to work out to be linear phase. This filter didn't work out particularly nice. We sampled and forced certain requirements on, and the ripples were kind of irregular looking, because in this design, it said, let's make the pass band, the first 4 points be 1, have a transition band of point number 4, and then have a stop band where we're going to tie it down to 0 at 3 more points. It was an arbitrary decision, but it was taking our degrees of freedom and just throwing that in to this matrix equation, having the different omega values where we're going to select to set an amplitude response and then see what it comes up with. This to me is a little bit like the arcade game, the whack-a-mole arcade game, which my sons played it a long time ago. I think they still have a game like that, don't they? So it's like you get to set certain things, but other things will pop up when you force certain things to happen. So here, the fact that the ripples were not all down nice and low was just like, didn't know what we were doing. We need to do it more intelligently. So I'm not a super big fan of the FIR frequency sampling design, but what I want to do now is look over here. This is in the notebook where I just did some examples very similar to what I was already doing in the notes. I just picked a bunch of different examples. I actually just sort of goofed around until I got, here I got a quadruplet. Here I just arbitrarily flipped the sign on some values to make it plus and minus ones. And this is really motivated by the fact that a moving average filter has all the coefficients equal to the same value, and that gives us a low-pass filter. So I know that if I multiply all the coefficients by minus 1 to the n in the Fourier domain, that would be a frequency shift of pi. Remember, we kind of ran into that, minus 1 to the n, cosine of pi n. Remember that in a homework problem? So sure enough, that's what this filter ends up being. It has the passband over here, and then it has a zero spaced around like that. So then here, what I did was I said, let's use some of the functions that I have in the FIR design helper. So I have a number of filters in there. And John was the first one to use it because he's taking the lab. These are I have the Remez equal ripple filters for low pass, high pass, band stop, band pass. And then I'm using another windowing function, which is a basic idea we talked about a long time ago of rather than just chopping something off, you taper it down with a windowing shape. And I'm using the Kaiser window, which gives a degree of freedom for setting a pass band and a stop band. So I do that Kaiser for low pass, high pass, band stop, and band pass, and then frequency response list is inside this for FIR filters and IIR filters. And then some other functions, the low pass order determination, things like that got added into this. SciPy.signal has got very powerful stuff. Don't think that what I wrote is super great. It was something that I wanted to do to get just what I wanted without having to do a lot of extra reading. But there are really nice things in SciPy.signal. So this was just my concept. So I design a filter here. Ends up being 53 taps, and it's a high-pass filter. So based on pole zero geometry and based on what we were just talking about for symmetric FIR filters, let's see if we can make some sense out of what we see here. First off, these zeros spaced around on the unit circle are obviously forming a stop band because they're trying to tack down the frequency response along the unit circle. That's where we sweep, so we're tying it down. Remember, we can do that at a finite number of points. And then it just so happens the way the math worked out right at DC, it solves out to be a conjugate reciprocal real zero. But then as it gets around further in this onto the back side of the unit circle, now we're getting what? What do you see there? Twins or quadruplets? So we're getting all quadruplets, which is kind of the more typical thing to form a pass band, where we're going to get, this pair here and here matches the ones up above, and then so on. There is one set on the real axes that are just real and symmetrical. And there's some extra ones packed right in here in the stop band.
And this would be type 1, right?
Yeah. So I was going to say, why is this, what is type, we know it's even symmetrical. We could look at that. But if it's even symmetrical, we don't have to have a zero here. But if there was a zero right here, then it would have to be a type 2, right? But for a high-pass filter, we don't want that.
Yeah.
So that's why it turned out this way. What would happen, there's what the response looks like, by the way. What would happen if I just flipped the switch on this and said, same number of taps, 53, but now just flipped it over or rotated it by 180 degrees. It's still identical. I mean, I know this because I wrote the code behind this. That's how it does it. It uses the low-pass design, and then it rotates it in order to get the equivalent high-pass. So there's no zero here, but we could do a bump on this. So let's do a bump. A bump lets you it comes up with an optimal design. It comes up with a filter length based on the requirements of the passband gain, stop band gain, the cutoff frequencies to go from passband to stop band, and then the amount of ripple in the passband, 0.1 dB, and then the attenuation in the stop band. It'll come up with a design, and then end bump allows you to shift the value that it comes up with. So if you go to the help for this, the default value for end bump is 5. So if I bring it down by a certain amount, I'm saying that is better for meeting my requirement. But I'll explain more on that in a second. Let's just change this by 3. And now it got a pole very close to 0. And whenever I see this, I'm suspicious that the polynomial routing routine may not have done things properly. I mean, I'm always suspicious of that. And people that write polynomial routing routines, have any of you ever wanted to write an algorithm to route a polynomial? I got involved with this a long time ago when I was running DSP software, but you'd have to take a numerical algorithms class from computer science to learn about how algorithms can be developed to route polynomials, but they all tend to have imperfections in them. They can fail to work, and as the order goes up higher and higher, there's more likely to be something that's going to blow up. It's kind of like running an engine up to a really high RPM. There's a chance you're going to have a rod blow a hole in the side of the engine. If that's a good enough analogy, I don't know. That's my way of thinking that you're getting too many routes to have to solve for, and there's a chance of it making a mistake. What I was hoping to do, that I would see something else, but this is the default value, 56. Okay, now this must be a type 2, right? Because we went from 2 to 5, so that was a shift of an odd number, 3, right? So we definitely have a type 2, and we can see there's a 0 right there, which is cool. So let's just see why I didn't want to go with type 5. Now I'm back on low pass, so I go back to high pass. I'll leave it on low pass. I requested 80 dB of stop band attenuation, and I'm exceeding that. So I'm saying I could bump it down because the algorithm's not really accurate for determining the order. So when I bumped it down by 2, or to just 2, and then I run this again, I can check the stop band attenuation, and this is pretty much right on it. It's much closer. Now you might think, if you're building an analog filter, I'll overdo my stop band attenuation because I'm going to have some losses in my inductors and capacitors in my lumped element filter, or some elements, analog elements. Good idea, but in a digital filter, as long as the precision is there, we don't have a problem. We will explore quantization in the next chapter. Chapter 6 looks at quantization. You'll have a homework problem where you get to play with that. Get to quantize the coefficients. And for this filter, which we just ran, this is the low-pass version as opposed to the high-pass version, but it's nice and symmetrical, has a center value. And if it's let me just switch this back because I'm trying to do too much stuff. Let me switch this back to bandpass. Or not bandpass, but high pass. Oops. I don't know, my finger hit too many keys for sure. That's supposed to be 0.22, right? 53, flips over, high pass. Now if you look at this, I guess I was hoping to be able to see that the DC response is 0, but we'd have to add this up. We'd have to see, in order to get this minus 80 dB, we learned this a long time ago. What is the DC gain of the filter would be the sum of these guys. I think that's right. If I take yeah, does that make sense? The ripple is 80 dB, it's down 80 dB, so I'll take the DC gain of the filter as the sum of the coefficients, take 20 log base 10, and I get minus 80, so that's that value right there. Okay, the last thing I want to do is I took a real design that was built for one of the microcontroller board, the FM4 board that John's been using. It's an ARM Cortex M4 running at 48 kilosamples per second, and the design of that filter is right here. It's part of problem lab 4, I believe. You did one of these filters, I'm thinking. So I designed the filter here. It has 60 taps. It again looks like kind of the classical linear phase design, lots of zeros around the unit circle, and then quadruplets sitting there. I used the network analyzer, the not Keysight, not Hewlett-Packard, but what's the name of the company? I can't think of. At any rate, we have those in the lab still, but they're pretty old and not in great shape. So I'll import that data here. And if you want to see what that data is, I can go over to here and I can look for L4. So this was it exports CSV data. And that's what I was doing. I was reading in the CSV data taken from the network analyzer. And I get frequency, I get real part imaginary, and real part imaginary for our second channel, but I'm just using a couple of columns, and then I'm skipping down to 16. So I skip 15 rows, and I use columns 0 and 1. And if I plot these two together, the measured is the orange and the theory is the blue. All things considered, I'm really happy with it. It looks pretty good. This is the way every lab should be. What do you think? I mean, over your experience, your seniors, did you always get good lab results? Picture perfect? But you had to explain why it wasn't perfect, right? So what maybe is going on here? Want to speculate? We talked about the A to D or D to A converter on these boards and A to D converter. You weren't here that night, but we were looking at the components that are in there. There's some RC elements. Maybe that's, that's over 20 kilohertz. Maybe there's some roll-off there in that analog interface. How would we see that? We would take our digital filter out and just connect input to output, and then do another sweep measurement with the analyzer, and then we'd be able to characterize what the analog components are doing. Does that make sense? So, but the ripple looks really good. Location of the ripples look pretty good. Okay, the last thing I want to do as it pertains to homework and as it pertains to the exam is I want to jump over this exam 2 examples document. Does everybody remember where that is? Or should I show you again? It's under course materials. This link right here. So I have that opened up right here. It has this as some sampling theory examples for being able to draw the pictures that I expect you to be able to draw, and there will be a problem that has you do something like this on the exam. And there's a couple of those in here. But then there are these designs at the high level where you take some H of Z and you want to synthesize it into minimum phase and all pass, or minimum phase and linear phase. And I'm not positive which I'm giving to you on this exam, but if I give you one type on this exam, the final will have the other type on it. So just as a hint, see that you can do both. So let's just take a little bit more complicated problem and work through this. Maybe I'll turn on my drawing tools over here. Okay, so if this is our system and we want to make this minimum phase and an all-pass section, what do we have to do? We have to look for all the zeros that are outside the unit circle, and they are going to move to the inside, right? So that's what's going on here. That's that zero. That zero, and that zero. So those zeros have to be put into the all-pass design as poles, and then the original zeros are stuck out there so that the cascade of the minimum phase and the all-pass becomes the original system. I think we have that down because we've done a few of those already. Suppose we want to take that idea and say that we can also do a minimum phase and a linear phase. So how do we do the minimum phase or the linear phase condition? Linear phase will be always, there will be a bunch of zeros or a bunch of poles at z is equal to 0 to balance off all the zeros you put in, because that's the nature of a linear phase filter. And then we have to think about how we synthesize that. So here, is everybody okay with this, or should I go to the easier version up above? Are you good with this? Okay. So we still move the zeros inside again. But, well, we don't move the zeros inside. We have to look at what is going on here and how we can represent parts of this as a linear phase. So ultimately, we want to get rid of the zeros out of our system, but we can put them in. The zeros that are outside the unit circle can be now part of a linear phase. So that's the zero. It gets moved into the linear phase, and it's balanced against that zero that's in the real system. So that actually forms a quadruplet. And then the zero that was outside here gets formed as a real axis zero pair at reciprocal locations. And now, how do we put this back together again? We have to make what we put into the minimum phase system sort of undo some of the things that the linear phase system has done. So we'll have to put in a pole to get rid of that, a pole to get rid of that, whereas it was done differently up here in the all-pass version. And then we have to put in a pole to get rid of that zero that was added, and then this zero will remain in the cascade. And of course, these other zeros in here were in the minimum phase version. And then sort of in summary, when you get done, you have to back away from this and say, okay, you have to count up how many poles you have, how many zeros you have, and then you have to add poles or zeros to the origin in each of these to keep everything in equilibrium. Is everybody, you getting that? So if I'm grading a problem on this, you have to make note of that fact. This will always have poles in it. It has to equal the number of zeros. And this will have zeros in it if you ended up having to add some zeros in here or poles in here to counterbalance the poles. So this is not going to be the same as in the minimum phase system for the all-pass, but for the linear phase, it changes up. So my hope is that you can look at this and just sort of digest it and see how it would work if you had to go this route. Understand though that linear phase system and all-pass system are two different animals. You'll have non-constant amplitude in the linear phase system compared to what you have with the all-pass system. So here it's more or less just a mathematical identity thing. You can generate another minimum phase system, but the frequency response magnitude of this system is not the same as this one because part of the original magnitude response is now synthesized over in the linear phase side. I'm just going by what I'm told by the books, I guess. I figured like you should know this, that this is another game you can play. So with the time that remains, I could either start chapter 6. I'm going to give you a really quick intro to it just so you know where we're headed, because we're taking a pretty radical shift going into chapter 6. And then I'll answer questions on projects, homework, and so on. And if you don't want to do any of that, then you'll be able to take off. So let's go over and do that. So if you were in a circuit theory class, you would think structures and circuit topologies are what we need to have. Well, digital filters and digital algorithms also have topologies. They're just in code, but they're still a topology. So we have structures for discrete time systems. So we get down to some of the obvious things will be direct form structures, cascade, and parallel. Probably our two favorite will be just direct form and cascade. Parallel is not as popular, but cascade is quite popular, and so is direct form. They have pros and cons. Cascade is the best for high-order IIR systems, and direct form is more popular for FIR systems. And then we have different topologies for FIR systems, too, to make them more efficient. This also maps into the implementation side, how to implement things that are the most efficient in terms of real estate, if it's ASIC, fabric cells in an FPGA, and I guess if it's in microcontrollers, how do you share clocks and things between different subsystems if you need them. So it starts off in a block diagram form like this, and then what the authors like to do, and which I like to do, will go with a signal flow graph, SFG, and that's kind of where things end up in this chapter when we go through it. Block diagram and signal flow graphs are very similar, but the flow graph is just a little bit more traditional. It's used in control systems. Has Dr. Plett been using them yet?
A little bit. I mostly remember this from circuits 2 though.
Okay. And then microwave circuits people and RF people use flow graphs for microwave networks, for S parameters and things. There's a very close connection between the two of them, so I've explored them both. But in microwave networks, you have forward and incident and reflected waves bouncing around in a system, whereas here you just have things going in one direction. But they still are useful just for different applications. There's theory and transposition theory and other stuff like that. So we'll be able to look at that, and we'll be able to make heads or tails out of, say, a non-standard structure. There's non-standard structures like this is a one-stage lattice filter, and what does it do? So we'll have to get in and write equations, kind of like you would node equations. We won't have mesh equations like you would have in circuits because we don't have current flow, but we do have a nodal type analysis, and that's what these equations pertain to, and we'll spend a little bit of time on that. This maybe seems like it's insulting you at the end of the semester to learn more different stuff, but this is not that far afield. I mean, it's pretty straightforward stuff. The only thing I'll say about this is if I know if I give kind of an unusual looking signal flow graph and you have to figure it out in the exam, it can be a choke time because you're just getting all balled up with stuff. The thing about signal flow graphs, though, or the block diagrams, is if somebody has written an algorithm and you are inheriting their code and you're trying to figure out what are they doing with this, you may have to take FPGA code or C code or something and just be able to decipher what it is, what did that person do. And my experience working with FPGA developers and wanting certain things implemented recently from my experience at ARCA is that the developers tend to make things pretty difficult for me to understand what they're doing because they think in terms of clocks and they think in terms of edges and things. When does a clock edge occur and when do we put some algorithm in? They think differently. But there has to be a way of communicating, and this is where documentation obviously comes into play. Over your lifetime, you'll be on systems that were documented really well. Somebody will say, this order filter is there. This is the coefficient that gets loaded into it. Other times, they'll be like, they lost that part of the documentation. Can you study the code and figure out what was implemented here? We have some clue. We have more clue. I mean, it can be all over the map. You know, you might find yourself pulling your hair out saying, what did they do here? Did they do it right? That type of thing. So that's what we'll be doing 2 weeks from tonight. We'll spend 1 week on this and get this out of the way, and then we'll do the DFT and the FFT in one night also, the last night of class. Now you're saying that seems so fast. Remember, we meet for 2 lectures, so I've done this before, and I know what to do and what not to do, and I know if things get tough, what I'll do to get us still home free. I mean, I know what I want to do. I'm generally not this relaxed at this point in this chapter, but I'm feeling like I should just not try to go into this right now. If you've got questions, or if you want to talk about Pi Audio Helper, because I don't want anybody failing to get that to work. So, do we have any more questions on what I've been lecturing on that I could do it live here, or just stop the recording and look at your code or look at your computers? What's your preference?
I'll look at my code.
Okay. I'm going to shut off the lecture. For those of you watching the video, we're not quitting for the night, but we are going to look at code running in real time on the Pi Audio Helper.